I think it's a fair time to go ahead and get started on our lecture for the day. So, today is all about doing something with that potential. Last two lectures, as we've been looking at them, we first started talking about the electric potential energy, which was kind of a natural extension from talking about the electric force, right? Anytime we've got some sort of force and a distance, we can get an energy out of that. So it seemed like a natural step to take in describing what's going on with different charges. However, when we looked at 25-2, we started talking about the electric potential. Not potential energy, but just potential. And that was a little bit strange. But we kind of reasoned with that to say, hey, well, the force had an electric field, which is what happens if you took away the second charge, right? It's like waiting for a force to happen. So what if we did the exact same thing to the electric potential instead? If we took away the second charge from an electric potential, the electric potential energy, what if we took away the second charge from an electric potential energy? Well, that's what we call the electric potential. It's an energy waiting to happen, which is a little bit less intuitive, I think, at first, but it's still doing the same thing. It's kind of a parallel concept. So, when we were looking at this in 191, or these types of ideas, we basically looked at everything to do with forces on its own, and then we looked at there are some places that forces don't do such a good job. For those, we will deal with energy instead. And we talked a bunch about energy. And then the last thing that we did, after we figured out how both of those topics work, we figured out how we combined them together, right? And we did that through work. We're going to try something similar today. But we're not going to do it with work necessarily. We're going to divide by Q. Let's imagine I have an electric field. And I want to go from point A to point B, and I want to find the potential difference, delta V, between those 2 points. How might I do that? Well, we might remember our old equation for work, maybe not, but we might remember our old equation from work, and to find that, we basically said, okay, take the negative integral of force.ds. I ran into the same issue last time too. There we go. Now I'm kind of like barely getting above the screen, but that's okay. But this was what we called a path integral. And we haven't talked about path integrals for some time now, but a path integral is essentially whatever happens when I have some field or something around me and I take a particular path and the direction of that path has some influence on how I solve the integral. In a case like this, we would see force dot ds, where ds is essentially a step in our path. Right? And we take all of these steps together and we dot them with the force that we feel at that particular step, sum up all of those things together, and that's how we found work. We didn't do it quite like that very often. We occasionally used a graphical integration method, and then sometimes if we had a uniform force and a path that was not going in all sorts of crazy directions, we could work with that as well. But for the most part, we didn't actually face the integral too much. But if we look at that integral and we say, okay, well, delta U is just Q times V, and F is just Q times E, and I divide by Q, I get rid of that second charge, I'm left with the exact same equation, but now it's relating potential with electric field. But it does the exact same thing, right? It's how I can find the potential difference if I know what a field looks like. So, this integral is a fantastic definition, and conceptually understanding that is wonderful, but this is one that we're not just going to only do graphically. We will do some of these integrals. So don't just neglect this equation right here. There are some easier cases though. If we have a uniform field, this becomes much, much, much easier to do, and you really don't have to do the integral at that point, because what you're basically saying is, hey, E.ds is a constant value. It's just the angle between them, right? It's just a dot product at that point, a very easy dot product outside of an integral. And then if S is going in some sort of straight path and E is always a constant kind of deal, then really this just turns into E dot S, where S is the length of my path. If we do it inside of a parallel plate capacitor, it's even easier, right? Because then the dot product is just 1 and we never have to worry about it. However, there's one thing that I've been neglecting to talk about, and it's this negative sign. And it's going to come initially from when we're thinking about something like how we actually found work. If I have any sort of object, I need to move myself back up here so that I'm not reaching super far above my head. If I have any sort of object like this, gravity is the thing giving me potential energy. But if I lift up, if I go opposite the direction of the force, the potential energy increases. That's why there's a negative sign. Now, how do we rationalize that when we're thinking about something like potential difference with electric field? Well, think about it like this. Let's think about our capacitor here for a second. Positive charges give a positive potential, right? If we remember from our point charge equation, it goes kind of like that. So over here, we're expecting to see high potential. Over on the negative side, we're expecting to see low potential. If we are going from the low potential to the high potential, so if delta V were to be positive, we're going against the electric field lines. So to make sure that they both go up at the same time, we have to put a negative sign there, right? If that makes sense. They're an opposing kind of relationship. As potential goes up, electric field goes negative. So I want to try this out. Let's look at the potential difference between, say, 0, 0 and 10, 0. So point A would be 0, 0 meters. Point B would be 10, 0. If those are the two values that we're looking for here, what is the potential difference first if the field was 700 I hat minus 600 j hat? And draw this out on a picture, please. Part B is going to be a little bit more weird, but I want to see if you can do it. All right, let's start to take a look. So this one's going to be a little bit weird when we get to part B, and I'm not going to do a very great job of drawing this thing out at all, but we'll get there when we get there. Let's draw out our axes first, and let's go ahead and label actually that we're working on 26-1. Our first problem from 26. So, and I'm going to draw this thing with a big x-axis because we're going from 0 to 10 in the x direction. Let's go ahead and label some things while we're at it. So my electric field, as we are told, is 750 I hat minus 600 j hat. I'm going to rotate this thing so I can draw these kind of efficiently, but not super well. My electric field is going to then look something like positive x, negative y, so maybe something a little bit more in the x direction. So maybe something like this, and a little bit something like this, and a little bit something like this. Not very great, but you know what? It gets the job done. So we're going to go from what I'm going to call point A out to point B. So our path that we're choosing here is going to look something like this. Go and draw some arrows on the end of that thing so we can see that. Now, as I take my step along the way, every single step, ds, is going to be somewhere along this path. So I can basically write it out here in purple. Here is my ds. What does ds look like in this problem? Any guesses from chat? What is ds? Realistically. It's not some crazy path. It's not constantly changing. Every step I take is going where? Now I do need another piece for that. It's not just dx. Because I'm looking at a vector. So I'm going to call this dx I hat. Going in the x direction, taking steps along x. Okay, then if I'm thinking about what's going on with my potential, delta V is equal to negative from A to B E dot ds. This is just exactly what we saw on the slide. So let's plug in the things that we know so far. 750 I hat minus 600 j hat. This is going to be dotted with dx I hat. And remember, what does a dot product do? It sums up together the individual components of my two vectors. So x components together, y components together, z components together, add them all. Here, ds only had an I component. So that means that the y component really doesn't matter here. Going from A to B, 750 dx. And remember, once we take a dot product, the direction goes away. I'm left with a scalar at the very end. So I've just got 750 dx. What are spots A and B? Well, I'm going from 0, 0, so 0x, 0y, to 10, 0, which is x is equal to 10, y is equal to 0. Doesn't matter anyways because I'm not plugging in anything for y. I'm only plugging in things for x. So in doing that, integral of 750 is just 750x. So negative 750 times x evaluated from 0 to 10, negative 7,500, 7,500, I guess. Negative 7,500 newtons per coulomb. Now, this was a more complicated way that this problem was done than it could have been done. Because what did I just say about constant uniform electric fields and paths that are relatively easy? All I would have needed to do is say that S is equal to 10 meters. The angle between these two is, well, I'd have to figure out what the angle was, but if I figured out what that angle was, then I could have just said that the potential difference is equal to the negative, I should have said negative E x component times S. I could have just done that. You right. I keep getting back and forth. The last problems that we do out of this are finding the electric field rather than the potential. We're still finding the potential. We should have units of potential. It should be volts. Thank you for the catch. But anyways, this problem could have been done very quickly, right? Realistically, I did absolutely take the long way around by doing the actual integral for this thing. We could have just said, hey, it's just a dot product. Take the x component, multiply it by the distance s, call it a day. It's a uniform field. There's no need to do anything else. And there isn't a need to do anything else. But if I do it with the integral, I think it's a little bit easier to see how we get this answer when we move to part B. So let's look at part B. I need to draw a new graph, and this picture is going to be awful, by the way. Do not take it for anything. It's hopefully going to be at least semi-accurate, but I want to just establish what this thing should look like, roughly speaking. So E is supposed to be 750x I hat. Y is going to be negative 600 y j hat. So my electric field then is going to look weird. So when I'm looking at, like, for example, along the y-axis here, I might see an electric field that goes like this, an electric field that goes more like this, an electric field that goes like this, an electric field that goes like this. From my x direction, it's going to start small and get bigger as time goes on. Something like that. For the in-between directions, it's a little bit strange. So I might expect to see something like that as time goes on, and something a little bit more extreme right here. Something like that, and these, kind of the same deal. Something like this. Right, so my overarching field lines look kind of like that, and kind of like that. But what's the point of doing all this stuff in the first place? It's to really remind you that, hey, this is absolutely not a uniform field. Not even close, right? This is going to be much more wacky than that, and I absolutely forgot to write in the x right there. X I hat. There we go. That's better. That's what that thing should actually be. It's not a uniform field. If we were to take the dot product of just plug in 10 somewhere, I'm not going to get the right answer. What we have to do is take the integral. So let's see what that looks like. Now, all of my definitions are actually still going to work just as before. I'm going from A out to B. My ds still looks the exact same as it did before. That hasn't changed. ds is still equal to dx I hat. So in doing that, I can kind of go along the same steps as before. I know that the y component doesn't mean anything because my dot product only has the x component surviving. There's no y or z components to ds. So we can essentially skip that step right there, right? We can just say, okay, well, let me immediately jump. The x component's the only one that sticks around. But this is now 750x dx. Taking another step down. I don't need this integral sign anymore. I'm about to get rid of that. I integrate 750x with respect to x. I get 375 x squared evaluated from 0 to 10. My final answer for the potential should be negative 37,500 volts. Now, keep in mind, in the Canvas questions here, this is given as it's asking for the magnitude. It's not asking for whether it's positive or negative. So put in positive 37,500. I did that mostly because if we get a little bit goofed up on which bounds to do or what should be positive or negative, or we forget that minus sign, any of that stuff, I wanted that to be okay. The integral and understanding that integral is the most important part here. Getting the negative sign at the very end is not a big deal to me. But that's what we would do. So, that's fine, right? We can go from electric field to potential, and we just have to take an integral. But we certainly just kind of brushed over some of the more complicated bits there, because what happens if our path is not so clean? Let's not think about that right now. Because it's a little bit easier to first describe how we would go from potential back down to field. If we see that it's an integral one way, it should be a derivative the other, right? Integrals are literally anti-derivatives. That's what they are. But we run into a little bit of an issue. And to describe this maybe a little bit more aptly, I'm going to use the tools that should be in every physics teacher's tool belt. Play-Doh and knives. So let's go ahead and form this into a nice solid ball for a minute. And if you have some Play-Doh in your house or any sort of clay or something moldable in the exact same way, I do recommend going and grabbing it real quick, right? Because this is a fantastic demonstration, I think. So let's say I'm going to make some shape in 3D, right? Which is why I have this thing and I'm not just doing this on a graph. I'm going to create what's called a saddle function, because it's a nice, strange thing to see in X and Y, and hopefully this is going to actually kind of hold its shape. It's going to have some rough edges, but we'll see what happens here. And I want to make sure that my face is close enough that you can kind of see what I'm talking about here. So let's get something just like this. I'm going to make myself just a little bit bigger, and I'm going to move myself up here in the meantime. Haha, there we go. So this thing is large enough that we can actually see what's going on. So a saddle function is just a three-dimensional structure that looks like a saddle, right? That's the namesake. So hopefully this doesn't fall apart in my hands. But something, oh, there's some nasty edges in this. It's not very clean. but it's something that looks like this, right? It is just like a saddle might look. Saddle function. So if we were to take a derivative of this shape, what is a derivative? It's the slope at a certain point, right? That's what a derivative is trying to do. So if I were to take some sort of object that is flat to try and find the slope, I might try and find it like this, right? However this lays flat, that's what the slope is, right? So I can't go through it or anything. I have to lay flat, relative to the structure to actually find what that slope would be. Now, the difficult part about this is for a function like this, I can imagine, so let me choose some x, some y. That's what my slope looks like right now, right? Going in these two directions. If I were to just scan over y, my slope changes. Maybe it doesn't change like this, but it is changing by spinning around like that, right? The flat part of the slope would be changing as I go around it. Now, I'm going to have a much more difficult time if I try and do it like this, but we can kind of see that. Now, if I pick some certain point then, and I scan along x now, we can see that, again, my slope changes. If I want to be flat relative to the structure, my slope is going to change in x and in y. I have a function that depends on both x and y. So, how can I find the slope of this thing at any given point? It's kind of difficult, right? Here's what we're going to do. This is where we bring in the knife. If I want to find what the slope is in the x direction, so if I'm calling this my x direction, this is my y direction, what I'm going to need to do is I'm going to need to pick y as a constant. I want to see how x changes. And to do that, I have to make a decision, and I have to slice through a particular point in the y direction. So I'm going to try and do this here, and it's, cut my fingers a little bit, but it's no big deal. For the sake of science, right? And we just cut that piece right off. Do you see what we have right now? This is a cross section. That looks like something I'd see on a graph. Here's my x. Here's my function. I can find the slope of a parabola. I can take a derivative of a parabola. I don't know how to take a derivative of the entire shape, but I can certainly find of just that cross-sectional area. Now, what if we had wanted to find the y component instead? Well, then what I would have to do is I would have to pick some x, and I would have to take a slice through it. And I am now losing more and more pieces of the thing as I go along, but my cross-section now looks something like that, maybe, right? And it should be the rest of a parabola again. But what we're basically saying here is to find the components of my slope. Because my slope is not just in one direction anymore, it's got x and y components, right? It is a sheet rather than a single line because we've got more dimensions. To find that slope, what I have to do is I have to, for a little while, pretend as if the other directions are constant. I pick a spot, I slice through it. That's what it means to find these derivatives, and that's what this picture on the front is trying to show us. That big red spot right here is our slice. If our three-dimensional shape in blue is sliced through at the red is the cross-sectional area that we see left, we can find the slope of that because it's in 2 dimensions again. We can we can deal with that. We know how to find derivatives like that. I don't know how well I can do it again. I would recommend go get some Play-Doh or some clay. Do it yourself, right? It's a really fantastic demonstration, I think. I love to do this one. And this is all of Calc 3, and I'm trying to do this in, smash a semester course into 10 or 15 minutes here. But that's what these equations are trying to do. And I know I'm still big. I'll fix it in a little bit. That's what these equations are trying to say, though. Take the derivative in the x direction, take the derivative in the y direction, and that gives you the slope in the x and the slope in the y. Then, if you wanted to create some picture of that, then I have a slope, a big plane, and that's how I would find the slope at that particular point. But I'm finding the x and y components of the slope. The curly fact, we could call that curly D. that means it's a partial derivative. That is the indication to you that there is more than one changing variable. So if there's x and y, it's partial derivative in terms of x, partial derivative in terms of y. But all that you need to do, it's not a complicated derivative. It's just a derivative like we've been doing this entire time up until this point. We're just basically saying, hey, if I'm looking at x, then everything else is a constant. Y, z, w, t, s, whatever other variables that I would pick. If I am taking a derivative in terms of x, everything else is a constant. Treat it like you would a constant. Focus on x. That's it. That's the entire thing. That's all of Calc 3 right there. Let me shrink myself back down to a reasonable size here and move back into my corner. So, the other things that we might see with that, because it's always going as a slope, the electric field will always point perpendicularly to the equipotential lines, and it always goes from peaks in the potential into valleys, right? The electric field would go from a positive charge to a negative charge, high potential to low potential, the electric field points down. It follows the slope down. So don't forget those negative signs. Now, one of the things that if you're watching Dr. Alexander's lectures that he's not going to include, and one of the things that people kind of maybe get upset that I include, move myself just a little bit so you can see that, is what we call the del operator. This is not actually anything crazy, I promise. It looks a little bit strange at first. It's not a number. That's one thing. An operator is not a number. I can't ever have a value for the del operator. The del operator will never be 3 or something like that. It's an operator, which means it is going to do something to something else. If I'm looking at what I've got down here, seeing this equation, E is equal to negative del V. That right there is just saying the x component is the partial derivative in terms of x, the y component is the partial derivative in terms of y, the z component is the partial derivative in terms of z. That's all. The nice part of it is that it takes 3 equations and it combines it into 1. So sometimes I might use del instead of dealing with x, y, and z just because it's so much cleaner. It's one equation, it's one line rather than having 3 separate lines. And I know a lot of people have not taken Calc 3. I know the majority of class has not taken Calc 3 and may never need to take Calc 3, but we still need some of the concepts for this course. We cheated and did some integral stuff in Physics 1, and now we're cheating again and using some Calc 3 stuff in Physics 2. It is a gradient. That is quite literally the name, right? Doing it like this is called the gradient. There are other things that happen with del, though. Actually, towards the end of the course, we will use del in a few different places for Maxwell's equations, because it's a very, very, very clean kind of thing to use, right? All it's doing is saying partial derivative and a direction. So if I want the partial derivative in x, put it in the x direction. If I want the partial derivative of y, put it in the y direction. It's just turning these things into vectors. So it's not any different from what we're seeing over here. It's just a much cleaner way to write it in, kind of a much cleaner notation to write these 3 equations, is to just combine it all into 1. That's all it's doing. So let's give this a shot. What I have here is the x component. I've got a potential, essentially, versus x. I am interested, what is the x component of the electric field? I don't know anything about the y direction. I don't know anything about the z direction. I don't care about either of those. I'm only focused on x here. Draw a graph of the electric field. Okay, let's go ahead and start taking a look at this. So, copy this thing over, and then I'm going to make it look really bad, because I'm going to draw a graph that doesn't match it super well. But that's what we're here for, right? My drawing skills are not what got me this job. So, let's go ahead and at least make it sure it's matching the same color. What I'm going to do is I'm going to draw another graph just beneath this thing. Something like that, and we'll put some little tick marks so that we have the same, roughly speaking, 10, 20, 30, something like that. Okay. We will label this as the electric field, or specifically the x component of the electric field versus x. Okay. All that we're really doing here, when you have a derivative of any sort over a line, it's a constant, right? That's all it is. It's just the slope. That's quite literally what it is. It's only when the slope is constantly changing that you actually have to go through the derivative process. Otherwise, we can just look at the slope. So, if we wanted to actually find what e is supposed to be, well, here in the first section, from 0 to 10, it's, wow, 0. That's it. Now, going from 10 to 20, our delta v in this particular region, let's go ahead and write this out. So, delta v is equal to a positive 200. Going from negative 100 to positive 100. So, our delta v is 200. Our change of distance, delta s, would be 10 centimeters, or 0.1 meters, which means that if I was to find the electric field in that particular region, E is equal to negative delta V over delta S. Remember that any time that we're talking about large changes, the dV ds becomes delta V delta S. That's really the only difference. dV just means infinitely small. So we plug those two in. 200 over 0.1 means that our electric field is negative 2,000 between 10 and 20. So let's go ahead and label it negative 2,000 newtons per coulomb. And then we'll draw those. We go back up to a plateau, connect them all so they look like one function all together, back to 0 for the rest of this thing. And that's it. How do we feel? Do we have any questions? It's negative 2,000 because remember, it's always the negative of the slope. So I would be taking my 200 as delta V. Go ahead and write this thing out. So it's negative 200 divided by 0.1, 10 centimeters. So convert that into meters so that we're all in standard units, and we get negative 2,000. Any other questions? A little bit more water before my throat gives out completely. You would think after doing this for so long that I would build up a little bit more of an endurance for talking this long, but for some reason my voice has just never had that much endurance. Is the X the same? Yes. Yeah, the tick marks are the same in both. I'm just trying to have it as a direct drop down. So 10 centimeters, 20 centimeters, 30 centimeters. Okay. Let's go ahead and keep looking at some of these things. So, that was a circumstance where we didn't necessarily really need to think about the fact that it's a partial derivative, right? We just had to say, hey, slope, and call it a day. Here, that is not going to be so simple. Our potential is constantly changing depending on where we're at in x and y. So, I want you to try and find, based on this potential, what is the electric field strength at 2, 2? What is the direction there? But even more importantly than that, I want you to have some sort of expression that would tell us what the electric field is at any point in space. It's actually not going to be that bad. All right, let's go ahead and start to take a look at this one. We saw my performance in the last drawing, right? I'm not going to try and do that. At least not 26-2, but 26-1. I'm not going to try that again, right? I'm not even going to bother trying to draw out this thing. Let me move that knife before I poke myself again. let's just go with the function, right? This is going to be with the one time. It might be worth it to draw the picture. Like, realistically, it is helpful. But I'm going to do a real bad job. So I'm not going to do that. So whiteboard 26-3, what we have is a potential that I immediately forgot to 150x squared, 200y. That's what it is. I always get those two backwards. So that's what my potential function looks like. And I'm going to do this in two separate ways that are really the exact same, but you'll see what I'm talking about in a second here. If I want to find what my electric field needs to be, I need to take partial derivatives in terms of every direction that I care about, right? So draw a little bit of a line here for myself. So I would say, okay, well, the x component is going to be the negative partial derivative of v with respect to x. Okay, so remember the process that we go through here. When we take the derivative with respect to x, every other variable that could possibly change is now a constant in our eyes. Only x matters. Everything else is a constant. So 200y squared, that's a constant value. What is the derivative of a constant? That's a question for chat, by the way. What's the derivative of any constant? 0. Always 0, right? So the negative 200y squared term, when I'm taking the derivative of x, doesn't matter. I'm only focused on the part that has x. So this will become negative 300x. Okay? Now I do the exact same thing for y. Negative dv over dy. But 150x squared. Now, x is a constant because I'm focused on what's happening to y. X is a constant. 150x squared is just a long constant. 0. The only part that matters is the part that has y. Now, if I wanted to make a full-on vector of this thing, whoops, that should be a plus, shouldn't it? Negative sign from before. That's, there's two negative signs. They should turn into a plus at the end. Here is what my electric field looks like as a full vector. Now, I'm not including z here because for the most part, we're only going to focus on x and y, but I could include z, but then x and y would both be constants and the z component would be 0. So there's not any z component to this one. Now, to find the strength, right? We need to plug in our values, right? So I'm going to take this equation that I've got for the electric field. I'm going to plug in 2 and 2. So x is equal to 2, y is equal to 2. Then I get negative 600 in the I hat direction plus 800 in the j hat direction. And our 3, 4, 5 triangle strikes again, actually. So if I've got two legs of the triangle, then the hypotenuse of this triangle, the magnitude of this electric field is 1,000 newtons per coulomb. Now, finding the direction, I'm going to draw out a tiny little thing so I can keep track. What direction am I expecting my electric field to be? I'm expecting I have negative 600, positive 800. So I would expect my electric field to be doing something like that. And I know that that point is not at 2, 2, but I'm doing this to find the direction, right? I'm thinking about my angle, theta. When I actually find that thing now, I'm going to take arctangent, which is going to be EY over E of X. Positives and negatives included. And if my calculator gives me something other than between 90 and 180, then I know something's a little bit off, right? That's why I wanted to draw this thing out in the first place, to give me an idea of what quadrant do I expect that to be in. Plug it in. What we should find is, oh shoot, I think it's 126.9. Where did it go? Where did it go? Where did it go? 126.9 is the final angle that we should find. And there we are. Magnitude of our electric field, angle theta. So the second method is really not any different, but I'm going to use del instead. And in doing that, here's what it looks like. E is equal to negative del phi. X component gets x derivative, y component gets y derivative, z component gets z derivative. We already talked about the z component. There is no z component in this problem, so that one's 0. Then I just have to look at these individually. If I were to take the x derivative, y would be a constant. If I was to take the y derivative, x would be a constant. And that's how I get to my electric field. It's going through the exact same steps. It really is. The steps here are no different. The only real difference is that del tries to combine it all together into one line, whereas the components you would have up to 3 separate lines. Del just puts it all into vector notation from the very start, rather than doing it at the end. That's the only difference. Functionally, they're identical. And then all the same steps follow from there. I think this one's most offending. Could try and make it look as clean as possible, but it gets you got to be careful with your handwriting. A lot of these. So the main difference is anytime if I only have one changing variable, then I would use the regular d. But anytime you see the partial derivative symbols, that's immediately an indication that there are other variables that are affecting the value, right? V is not just dependent on x, but it's dependent on x and y, or maybe x, y, and z. So, all right. So, in a lot of these problems, the reason that we have these different methods that tie things together is because realistically, some problems are very difficult and sometimes there are easier ways to get to the final answer, even if it's not as straightforward, right? This is a common theme in a lot of physics and math that we don't want to necessarily get directly to the answer. Sometimes it's worth it to take the long route because it's a nice, easier path to get there. One example would be finding the electric field. What if finding the electric field is very nasty? What if we have some weird shape and we have to think about how do we integrate r hat and other nonsense like that, right? Those were not easy integrals to do, but the potential integrals are at least a little bit easier, right? Because they don't have direction to contend with. They've just got to deal with the scalar values at any point in space. And so with something like that, it might be easier to find the potential of an object and then take the derivative to find the electric field. And the way that you would do that, if you're looking for a particular point, is an equation that looks just like this, which is almost no different. It's got this vertical line at P. And you might be used to seeing this in integrals. At the very end, you've done the integral, now you're evaluating the integral. That applies to more than just integrals, right? Basically what we're saying here is that the electric field of x is equal to the negative partial derivative of the potential as with respect to dx, which is a long thing to say, evaluated at point P. Take the derivative, plug in the values at point P. What happens if you plug in point P first? What do we think? If we go to any of these problems, if I plugged in x is equal to 2 and y is equal to 2 and then took the derivative, what would I get? For my electric field, at least. 0. What if I plugged in 4, 4? I would get 0. You can't plug in the constants before you take the derivative. You have to take the derivative first, and then you can plug in the constants. Right? So keep that in mind. That's why we write it out like this. This is saying take the derivative and then plug in the number. You have to do it in that order. So, here's a fun one. I've got this kind of mess of a graph. I've put some different charges in random spots, and I've got all of these cool-looking equipotential lines going throughout this chart. Right? And they've all got a label somewhere on them. This is not an exact problem, but what I want you to do is to estimate the direction and strength of the electric field at that point A. All right. Time to start taking a look here. So, there's a few different details that are going to be helpful in here. One of the ones, and it's something that I know I glossed a little bit over when we were first talking about it, but I think it's a little bit easier to talk about it now that we actually have a graph in front of us. When we're looking at something like an equipotential, and we're trying to think about the electric field, there's one big point, and it's that E is always going to try to be perpendicular to those equipotential lines. So let's go ahead and take this thing and let's copy it over so we can draw on this thing a little bit more. And I'm just gonna, let's move it a little bit. Let's take this thing up here. So if I was to think about what does the electric field look like at any point, and before I dive too far into it, I really could just look at a lot of these different things and say, hey, I see the collection of charges and I can take an educated guess. Even if the equipotential lines weren't here, I could take an educated guess as to what the field lines would look like, right? It's going to be coming off from the positive charges towards the negative charges, so maybe like that, and maybe like that, and like that, and something like that, and something like that, and then maybe like a big one that goes around like that, right? Roughly speaking, and that's not super far from the truth. And let's look at those lines that we just drew. With the mishaps of, besides my shaky hands, we can kind of see that for the most part, not super well, but the electric field line is almost always trying to be perpendicular to the equipotential lines. And in reality, they should be. I'm just not a fantastic artist. So that tells us immediately a few things about what's going on with our electric field, right? We can almost immediately start thinking about the direction, because if we're focused on what's going on at point A, I'm only going to think about the closest two equipotential lines, negative 4.2, negative 7.5. Let me take a path going right through it between these two. So as close as I can get perpendicular from one directly to the other, roughly speaking. It's not great, but it works. Here's my path, and I'm going to set this point. Here is my part A, here's my part B. These are both in green. This is the path that I take from A to B is my S. We're not asked to find exact values, and we're not gonna right now, realistically. What we're gonna do instead is we're gonna take approximate values. So in taking approximate values, here's what I can say. Let me take S, let me not treat it as an integral, but let me just pretend it's a uniform field for a little bit. Let me take this direction S, though, and let me make something like this. Let me just say, okay, well, the magnitude of E would be equal to delta V over delta S. Let's think about that. Delta V is going to be, well, my final is negative 7.5. minus negative 4.2. It's a little bit messy, but what we get is that I have a ending negative 3.3 volts. Oh, whoops, there should be a negative sign here, shouldn't there? Let me plug those values in. And the way that I'm looking at this, I need to zoom in for a second. Let's do this in this kind of red color real quick. So I'm going 2 over, I'm going 2 up. If we look at our legend here, each little square is 1 centimeter. So 2 centimeters over, 2 centimeters up, that's 2 root 2 as my, 2 root 2 is my distance, delta S. Zoom back out just a little bit. So 2.8, or I guess 2.83 centimeters, 2.828. So 2.83 centimeters is my delta S. I've got negative 3.3 volts that I'm plugging in here. So negative of negative what we find at the very end is if we have plugged in these numbers, let me just go ahead and calculate this out. Actually, it's probably the fastest way. Rather than searching through where I wrote it down, I'm finding something like 116.6. Newtons per Coulomb. And let's think a minute about what it means to be positive or negative. If I was negative, that would imply that relative to the direction my path is going, my electric field is going in the opposite way. So if I'm looking at this thing and I find a positive answer, well, then I could say, okay, well, then my electric field goes along with the path that I picked, right? Which we drew at the very beginning, something like this. We were expecting to see an electric field pointing in that direction. And I said 2 and 2 because it's roughly speaking, so I'm going to say about 45 degrees, and this is about the magnitude of my electric field. And again, these are all approximations and estimations, but that's roughly how you could do it. You don't need to have necessarily all of the exact information. This gives you a rough idea of what the electric field is in that region. Does everything I've said make sense? Delta S, I was looking at the distance between these two equal potential lines. I basically said, hey, what's the slope at this particular spot? Right? It's more like when you're doing the calculus at the very beginning and you're taking a bunch of different trapezoids and everything, and you're not taking the true derivative, you're taking the limit. And you don't take the limit all the way to infinity yet, or 0, I guess. You take it so that it's at some, 1 centimeter spacing, and you find the slope of that, and you say, okay, well, the average slope between these 2 points looks like this. That's exactly what we're doing here. Now, we just have a, multi-dimensional function. So I can't just look at one single graph. I've got to look at this big mess of all these different lines and say, okay, well, I'm still taking an approximate slope, an average slope between these 2 points. So I'm going to take the change in height over the change in distance, and that's my electric field. Remember that anytime you go larger than infinitesimally small, your dV ds becomes delta V delta S. Right? Any derivative over a large space is really just a slope, and that's, our old slope equation, delta y over delta x. When you take it infinitesimally small, becomes dy dx. Same thing here. But there's like a lot of creative freedom in this. You've got to pick some points, right? And you just got to kind of go with it. And everybody's might be a little bit different, depending on how exact they were or which points they picked exactly, but around 116.6, that's about what I'm finding. Okay, we've only got one more problem for today, though, so let's go ahead and take a look at it real quick. This will be a pretty short one. And this is one that you actually already have the answer to because we did it in chapter 23 as an example, but nonetheless, you know what the answer should be. The potential from a disk of charge at point P, somewhere along the axis poking through that disk, looks like this big nasty equation. Take everything that you've just learned. What is the electric field based on this equation? Go through the steps. You know what the final answer looks like. There's no use in just plugging in what the final answer should be. Go ahead and solve it out. You know what the answer should look like, so it's better practice that way. You know if you've got the right answer. All right, I'm going to say let's go ahead and take a look at this, and we'll close out our day with this one. So this one will be kind of quick. We're going to take this thing, and I'm interested in the z component of the electric field. But if we look at this thing, there's only dependencies on z, right? So the x and y components we already know would be 0. If we took them, the entire thing just behaves like a constant. E of x is 0, E of y is 0, E of z is the only one that's left. So let's work with it. Electric field is equal to the partial derivative of v with respect to z. Okay, q over 2 pi e naught r squared. That's a really long constant. Doesn't get affected. Not worried about it. I'm actually a lot more interested in what's inside of the brackets here. So I'm going to we'll go ahead and leave this thing in place for now. So negative q over 2 pi e naught r squared times, okay, I'm going to rewrite this real quick. So let's do this in dark gray. This is r squared plus c squared to the 1/2 power. And I just do that so it's a little bit easier to see when we have to go through chain rule for this thing. Chain rule would say, okay, bring down the 1/2 times whatever was inside, you know, minus 1/2 now, subtract 1 from it, and then multiply that by the derivative of what's inside. R squared, constant. Z squared, not a constant. So multiply by 2z. And then the derivative of z is just 1. Okay, simplify it a little bit. What we would get inside of here, the 1/2 is going to cancel with the 2, and I've got 2, not 2, z, there we go, over, let me make that a little bit more of a straight line, so it's not just constantly sloping down, z over square root of r squared plus z squared, minus 1. Take a couple steps here real quick. If we're remembering what the equation looked like on the equation sheet, it depended on eta, not on q and r squared. So let's do this real quick. Let's say, hey, remember that the surface area density would be the total charge divided by the total surface area, pi r squared. And then I'm going to move the negative sign to the inside of this function. So now I'm going to label that, that's e of z, is equal to, let's see here. Let me make sure that I don't lose track of anything. Eta over 2 e naught, 1 minus, do the square root first, and it's the exact same thing that we had on the equation sheet. And that's it. Well, I think with that, we will close out the 26-1 lecture.